Hello, my name is Rula Nassif from the Decentralized laboratory at University of Côte d'Azur in France. Welcome to this IEEE webinar on decentralized learning over multitask graphs. In today's webinar, I will be presenting a collection of collaborative research works on the topic of decentralized learning over multitask graphs. In particular, and as collaborators, I would like to mention Stefan Vlasky from Imperial College London, Ali Sayed from EPFL, Cédric Richard and André Ferrari from University of Côte d'Azur, and finally Ji Shen from Northwestern Polytechnical University in China. Please feel free to ask questions during the Q&A session at the end of the webinar. With that, I think I'm ready to start this webinar. Today, network systems are everywhere. Smart grids, transportation networks, and social networks are some typical examples. These systems consist of a collection of nodes or agents distributed over some geographic area and connected by a topology or a graph. These agents are collecting measurements in a continuous manner, and the objective is to extract some global piece of information from processing the locally collected data. For example, in smart grids, the objective would be to estimate the power system state in the grids. There are two main modes for processing the data. We have what we call the centralized mode and the decentralized or distributed mode. In a centralized mode, agents send their collected data to a fusion center. The fusion center processes the data and then sends the results back to the agents. The centralized implementation, however, suffers from some limitations. First, it may suffer in terms of robustness, since any malfunction in the fusion center can lead to a network breakdown. Second, it requires high communication resources, especially when the data is collected in a continuous manner. So in this case, the data needs to be exchanged back and forth between the agents and the fusion center. And finally, in some situations, we might have privacy concerns. In such cases, sharing the data remotely with a fusion center can be considered as a violation of the privacy of the network. On the other hand, in a decentralized mode, the agents that are connected by a topology are only allowed to exchange information with their neighbors and to perform local computations in order to achieve some network global task. So, for example, agent K in the figure is only allowed to exchange information with the agents 1, 2, 4, 6, and 7, and to perform local computations in order to achieve some network global task. Now, the existing literature on decentralized learning focuses on single-task networks where all agents need to converge to a common parameter vector W0. The agents in the network, in this case, need to reach a sort of consensus on that parameter vector or on that task, which is W0. We have many proposed solutions for solving single-task problems in the literature. Among them, we have the diffusion strategies, which are attractive since they are scalable, robust, and enable continuous learning and adaptation over networks. Take, for example, this single task application. Here, all the agents in the network would like to get to a target located at the center of the figure. At the same time, they would like to avoid some dangerous area, which is the area in red. Each one of these agents has noisy measurements about the direction to the target and about the distance to the target. In principle, each one of them can just use this noisy knowledge to get to the target and to avoid the dangerous area. But if they can collaborate together, they can improve their own estimates. Today, we are witnessing a growing interest in multitask or heterogeneous network, where each agent in the network has its own objective and is interested in estimating its own task or parameter vector W0K. In this case, if the tasks are related, exploiting the similarities between them can lead to better estimation results. Another type of multitask network is this clustered multitask network. In such networks, nodes are decomposed into clusters, and within each cluster, all the nodes are interested in estimating a common parameter vector or a common objective. In this case, the objectives at neighboring or connected clusters are assumed to be related so that cooperation between the clusters can also be beneficial here. So if we take this example here of clustered multitask networks, we have Q clusters. Nodes belonging to a given clusters are represented by a given color here. The objective of the nodes in a cluster is to get to a target located on the arc of circle here. Since the targets are close to each other, we expect that cooperation between the clusters can be beneficial to reduce the impact of the noise in the measurements. Depending whether the composition of the clusters is known or unknown, we distinguish usually between two main scenarios for multitask learning. We have what we call the unsupervised scenario, where the decomposition or the composition of the clusters is unknown. In this case, clustering algorithms are derived in order to limit cooperation to nodes sharing the same tasks. In other words, we are interested in performing automatic clustering. The second scenario for multitask learning is the supervised scenario. In this case, the composition of the clusters is known and the relationship between the different tasks in the network is known. The objective in this case is to derive multitask algorithms that use the prior information on how the tasks are related. In this webinar, I will focus on multitask learning over graphs in supervised settings, where we assume that we have a multitask graph with some prior information on the relations between the tasks. I would like to note here that many works in the literature have considered decentralized multitask learning in supervised settings. A review paper titled Multitask Learning over Graphs, which is here, was recently published in the IEEE Signal Processing magazine. So for those who are interested in the literature overview, they can check the references appearing in the magazine paper. Now, among many possible task relatedness models, I will focus here on explaining three important problems. The first one is multitask learning under smoothness. The smoothness here is with respect to the underlying graph. So this setting is important since it shows how we can incorporate graph-based priors into the learning problem. The second problem is multitask learning under subspace constraints. This setting is also important since it shows how to perform network-based subspace projections in a decentralized and iterative manner. And finally, I will show you how decentralized projection and graph-based multitask learning can be combined together to solve an example of a clustered multitask learning problem, where the composition of the clusters is known. Before considering each problem alone, I would like to summarize the framework for learning over multitask graphs. Remember, we have a collection of n nodes or agents. Each node is interested in estimating its own parameter vector or task W naught k. This task corresponds to the minimizer of a cost jk associated with agent k. The cost is given as the expected value of some loss qk. The expectation here is computed over the distribution of the data xk. Node k does not have knowledge of the distribution of the data or the cost jk. The estimation in this case of the task W naught has to be done in a stochastic setting where the exact knowledge of the gradient is not possible. So in general, node k can estimate W naught k without cooperating with other nodes. But since the tasks here are assumed to be related, cooperation here can be beneficial. So the cooperation rule will depend, of course, on that prior information on how the tasks are related. Now, to design the cooperation rule, we need here to formulate a global cost function that allows to promote the relationships between the tasks and then to solve this problem in a decentralized manner. In general, the global optimization problem is of the form written here. We aggregate the costs from across the network, and then we add to them a regularization term. The eta here is what we call the regularization strength, and the R of W is the regularization function. Now I'm using here the calligraphic W to represent the vector collecting all the parameter vectors from the network. The form of this R of W is directly related to the available prior information on how our tasks are related. And also, depending on this prior information, we might end up with a problem where the calligraphic W is required to lie in a convex set omega. I will show you some examples in the following presentation. Now, when we tried to propose a unified framework for multitask learning, we observed that the majority of the existing decentralized multitask strategies have a common structure. They mainly consist of two steps. The WKI here that you are seeing is an estimate of the task W naught K at node K and iteration I. The psi Ki is an intermediate estimate. The first step is what we call the self-learning step, where node K performs a stochastic gradient descent on its own cost Jk. The mu that you are seeing in the first equation is what we call the step size. It's usually a small positive parameter. Instead of using the true gradient vector, as you can see, we are using an approximation of the true gradient vector. So it's common in the literature to use the gradient of Qk as an approximation, since the gradient of Jk is unknown in a stochastic setting. The second step here is what we call the social learning step. In this step, node K collects from its neighbors the intermediate estimates and combines them according to the function Gk here. This function acts as a steering function. It tells the nodes how they should cooperate in order to point in the right direction and in order to improve their own performance or the performance of the network. The form of this function is directly related to the form of our regularizer R and to the convex set omega. Now, it's important to note here that the rule is fully decentralized, since node K needs only to collect from its neighbors their intermediate estimates. Let us start by learning under smoothness. I will present the global idea and I will highlight the main or the important concepts. For the technicalities, you can check the works learning over multitask graphs and a regularization framework for learning over multitask graphs that appeared in the IEEE Open Journal of Signal Processing and in the Signal Processing letter. Now, multitask learning under smoothness arises in weather forecasting application, for example. In this application here, we have 139 weather stations. They are distributed across the United States. The stations are collecting daily measurements of the weather. The data is collected from 2004 till 2017 each day. The objective here is to predict at each weather station if it will rain or not. Gamma K is the variable associated with rain occurrence. It takes the value +1 if it rains and -1 if not. HKI is the feature vector associated with node K and time I. Its entries are the weather measurements, such as the temperature, wind speed, and so on. So given the features H and the labels gamma, each station can use an individual logistic regression machine in order to find the hyperplane W naught K separating the classes. The task in this case is the minimizer of the regularized cost here that you are seeing. So in this application, if two weather stations are close, we expect that the decision rules W's to be similar. So to formulate the multitask learning problem, we assume that a symmetric weighted adjacency matrix C is associated with the graph. The entry CKL of this matrix is positive if node K and node L are connected. The CKR here reflects the strength of the relation between the two nodes. In the smoothness prior, the network vector, which is the collection of the individual vectors to be estimated, is smooth with respect to the underlying network topology. We let L denote the graph Laplacian, which is defined as D minus C. D is a diagonal matrix with the entry K given by the sum of the entries on the kth row of C. The smoothness of the calligraphic W can be measured here in terms of a quadratic form of the graph Laplacian W transpose LW. The Kronecker I that you are seeing here is here to handle the vector valued variables at Z nodes. This W transpose LW can also be written as the aggregate cost that you are seeing here down. The smaller the R of W is, the smoother the signal W over the graph is. So if we take a look to the expression here, since the weights here are non-negative, the expression of the R of W shows that the W is considered to be smooth if nodes with a large CKL on the edge connecting them have similar tasks WK and WL. When we have the prior that the vector collecting the minimizers of the JKs is smooth over the network, we can add this W transpose LW as a regularization term that we want to minimize in addition to the aggregate sum of individual costs. Eta is the regularization strength that will control the learning process, as we will see. So if we use here the stochastic gradient algorithm to minimize the global cost with some incremental step, we will arrive to the multitask algorithm that you are seeing in the two equations here. You can check the paper for more details. The second step here is the social learning step. Node K receives the size from its neighbors and combines them according to the social learning step. It's important here to observe that the combination coefficients depend on the entries of the adjacency matrix CKL, the step size mu, and eta. This dependency on eta will allow to control the steering function in a multitask mode of operation. So if eta is equal to 0, we don't get cooperation between the nodes. In this case, each node minimizes its own cost. If eta goes to infinity, we are in the single task mode of operation where the nodes cooperate in order to reach a consensus on the estimate while minimizing their individual costs. And by picking a positive value of eta that is finite, we are in this case in the multitask mode of operation. When we studied the approach, we derived closed form expressions for the performance in steady state. I will not go into the details here, but I will use the derived expressions in order to point out how the graph influences the performance, how the data characteristics influence also the performance, and how the step size and the regularization parameter mu and eta influence also the performance. Remember here that the objective at each node is to estimate this W naught K. Under the prior information that the collection of the minimizers is smooth with respect to the topology given by the adjacency matrix C. So instead of minimizing the individual costs only, we added a term to promote the prior information. We derived an algorithm for solving this regularized network problem. Now we need to study the performance of the algorithm with respect to the original minimizers W naught K. It can be shown that the steady state mean square error with respect to W naught can be expressed mainly as the sum of two terms, as you can see here in the bottom. We have the first term, which is the steady state mean square error with respect to W naught eta. W naught eta here is the solution of the regularized problem. This is the variance term. The second one is the squared norm of the difference between the regularized solution and the unregularized one. This is the bias induced by or from the regularization. To see what these expressions are telling us, we considered here a simple network example of 15 nodes. In these examples, all the nodes have the same hashes and the same noise covariances. So we are in a sort of a uniform data profile. The x-axis in this figure on the right represents the eigenvalues of the Laplacian matrix. And as y-axis, we have the values of the individual terms, which we called MSD of lambda m. We consider different values of eta, as we can see from this plot. For a fixed eta, as the lambda m increases, the values of the corresponding MSD gets smaller. And for a fixed lambda m, as eta increases, the values of the MSD decreases. This reminds us of a low-pass filter behavior. The eigenvalues of the Laplacian are interpreted here as the frequencies, and the eta controls the sharpness of our filter. And if you look to the black stamps here, these stamps correspond to the noise in all frequencies. It is as if we have a white noise over the graph. It exists in all the frequencies or eigenvalues. By picking an eta different from 0, the algorithm will start filtering the noise, and the sharpness of the filter will be determined by eta. Now, if we go back to the mean square performance with respect to our W naught, we still have to study the bias term here. This bias term is more likely to increase when eta increases. However, we expect that for sufficiently smooth W naught, this term will remain sufficiently small. This is actually true. To see this, we took a look onto the solution of the regularized problem. For each eigenvalue of the Laplacian lambda m, we took the corresponding eigenvector Vm and computed the product between Vm and the regularized solution. The Kronecker I here is to handle the vector valued variables at the nodes. The obtained values are illustrated here as y-axis, with the x-axis the eigenvalues of the Laplacian. Again, we observe a low-pass filter behavior. The dark stamps correspond to the spectral content of the minimizers of the individual costs. In this example, we started with a signal that is 1 for all lambdas. Then we started increasing our eta. It can be observed here that for a fixed eta, as the lambda m increases, the squared norm of the corresponding spectral content decreases. And for a fixed lambda m, as eta increases, the spectral content decreases. So lambda m can be interpreted as the frequencies and eta the controller of the sharpness of the low-pass filter. Now, if we consider again the smoothness measure R of W, by doing the eigenvalue decomposition of the Laplacian, we obtain sum of n terms here, each corresponding to one eigenvalue. Remember that the smoother the signal is, the smaller R of W is. So since the Laplacian has one eigenvalue at 0 and the remaining eigenvalues strictly positive, so for R to be small, the spectral content corresponding to large lambda m has to be small. And since from this plot we know that larger lambda m's are penalized more than small lambda m, we expect that when W naught is smooth with respect to the graph, we can find finite values of eta that can ensure very small bias. Therefore, by increasing our eta, the variance term is more likely to decrease, which is the first term. The bias term is more likely to increase, and the size of the increase will depend on the smoothness of the minimizers. We can plot the variance curve to the right, eta on the x-axis, MSD on the y-axis. Here, we have the point where eta is equal to 0. By increasing the eta, the error decreases to a point here. It corresponds to eta equal to 4, where it attains its minimum. Then by increasing eta, the error increases because the bias term starts to be large. So we can finally conclude that as long as W naught is sufficiently smooth, finite values of eta exist such that the bias of the regularization will remain small and the performance of the network will improve compared to the non-cooperative solution. Returning now to the weather forecasting application, remember that our objective was to construct a classifier at each weather station to predict if it will rain or not. We constructed a graph based on the geodesical distance, and we used the 4 nearest neighbors concept in order to put the links. So we use as training set the weather data from 2004 till 2012, and as test set the data from 2013 till 2017. We applied our algorithm, and we found that the prediction error is the smallest for eta equal to 45. Here, we picked a day from the test set, and we illustrated the real case and the predicted case. As you can observe, the predicted values are good enough. Now, can we do better regularization-wise? The answer will be yes, but to obtain a better variance bias trade-off, we will need to add a degree of freedom at the level of the regularization, which may require performing more communication steps at each iteration, as we will see. So while in the previous case, eta, we used it in order to control the sharpness of our graph filter, here we will use the graph spectral regularization in order to add this degree of freedom and to control the shape of the filter. So instead of regularizing using our L, we will regularize using a function of L, which we denoted as R of L. This function R will take as arguments the eigenvalues of the graph Laplacian. So the notation R of L that you are seeing in this slide is for a matrix function. When we will apply it to L, it is as if we are applying it to the matrix lambda, which consists of the eigenvalues of our graph Laplacian. It's a diagonal matrix. This regularization framework usually allows us to use the Laplacian in order to construct some meaningful regularization function. So to ensure the convexity of the optimization problem at the end, we need to choose the function R such that it's non-negative. So as you can see in the box here, we added a degree of freedom to the penalty term. We have eta now as the regularization strength. We have the R as the regularization function. Now, by replacing L by its eigendecomposition V lambda V transpose, we can write the equations in the bottom here. On the left, we have the graph Laplacian, which can be written as the sum of n terms, each corresponding to one eigenvalue of the graph Laplacian. The W bar n here is the spectral content of the network parameter vector at the eigenvalue lambda n. It can be obtained by multiplying the network parameter vector by the eigenvector Vm, corresponding to this mth eigenvalue. When we add this term as a penalty, we are penalizing now the m spectral content of the network parameter vector by the coefficient lambda m, as you can see. On the other hand, when we use the graph spectral regularization here, we penalize it by the function R of lambda m. This is an added degree of freedom, of course, that will allow us to control the spectral content of our solution. Now, how to choose R in the smoothness case? Remember, in the smoothness case, the entries of the parameter vectors are smooth with respect to the graph, as we described before. So nearby nodes will have similar tasks or minimizers. So if we take the example here on the left, we have a graph of 50 nodes. Each level here corresponds to the distribution of one entry of the parameter vector over our graph. So each node here will need to estimate 4 entries in this example. To the right here, we have the spectral content of the network parameter vector, W naught, to be estimated over the graph. So for each eigenvalue lambda m here, we compute the inner product between the corresponding eigenvector V of Vm and the network parameter vector W naught. Now, since the W naught is smooth, we obtained a distribution of the spectral content that is non-zero for small lambda m and 0 for large eigenvalues. This behavior is usually common in the smoothness case or smoothness assumption. So in the smoothness case, it's clear that now we need to choose our R of lambda such that R of lambda m is large for lambda m that are large and small for small lambda m. This choice of R of lambda will lead usually to small estimation bias. Therefore, in the smoothness case, we should choose a monotonically increasing function in lambda. Now, in this slide, we list some examples of R. So we have first the Laplacian with P, an integer greater or equal to 1. So R of lambda in this case is lambda to the power of P. We can see from the figure how the lambda squared or lambda to the power of 3 penalizes less the low eigenvalues and more the large eigenvalues when compared to lambda with P equal to 1. Therefore, we should expect now that the lambda square regularizer would perform better in the smoothness case than the lambda to the power of 1. We have of course, other forms of monotonically increasing R, such as the band-limited one. In the band-limited case, we would like to set R to 0 in an interval of eigenvalues and to a positive constant beta for other values of lambda. Therefore, by properly choosing the interval B in this case, we obtain a zero bias scenario if we choose the discontinuous regularizer. So while bias-wise this regularizer can be optimal, it has one disadvantage in the decentralized implementation, as we will see in the next slide. Now, when we try to derive a decentralized solution to solve the regularized problem using the stochastic gradient descent approach, and when the simple L matrix is used, we get a decentralized implementation since the Laplacian operator by default is local, and if we want to implement L times a vector W, we can do it locally by communicating with our immediate neighbors. So as you can see from the equation here, that node K can obtain the K subvector of Y by combining the WLs from its neighbors. CKL here are the entries of the adjacency matrix. Now, if I have a function L squared instead of L, I can write the product as L times LW. In the first hop, I do the LW, and then I apply the operator L a second time, but now to the result LW, so I can get L squared W. The operation is still local, but instead of requiring a one-hop communication, we need two hops now. In the case of L to the power of P, I will need P hops to communicate in order to implement the product LP times W. I can implement in this way any polynomial function in L or lambda. I just need to combine the terms properly. If the higher order in the polynomial is S, then I will need S hops to implement the product R of LW. As a conclusion, when my matrix R of L is polynomial in L, I can minimize the cost in a decentralized and iterative way by performing S hops at each iteration. Finally, we can write an algorithm as the one listed here to minimize the regularized cost. We still have a self-learning step to learn from our data, and then we have as social learning steps. These steps are performed, of course, sequentially. Each step will generate an intermediate vector psi s, and then the psi's will be combined locally to generate finally the W, the required W, which is the estimate of the solution at node K and iteration I. This algorithm actually tells us if we have R, a polynomial in lambda, I can implement the solution in a decentralized manner. The smaller S is, the less the required number of hops will be. Now, for a non-polynomial R, we can use the theory of polynomial approximation, such as the Chebyshev polynomial approximation theory, to approximate a non-polynomial function by a polynomial one in lambda or L. The problem is well known in the graph signal processing literature or domain. There are actually many works that focus on designing decentralized graph filters. So from the polynomial approximation theory, we know that a low-order polynomial can approximate well a continuous function, but for a discontinuous function, we need a high-order polynomial, which can be problematic in a decentralized implementation since we will need to perform a large number of hops at each iteration. So in this case, for a discontinuous R, such as the band-limited regularizer, it might be better or wiser to use projection-based method instead of this regularized approach. We will see how we can project onto the range space spanned by the first eigenvectors of the graph Laplacian in the next part of this webinar. Now, performance-wise, and since in this framework, what we did is we replaced L by R of L, we can use the previously derived theory in the current generalized framework. We only need to replace, of course, L by R of L and lambda by R of lambda. So as I explained before, we can now have a control on the shape of the filter. By considering now this network where we need to estimate a smooth signal of 4 components at each node, you can see from the components of the MST bar here at different eigenvalues how the R allows to have different filter shapes. This freedom in choosing the R is important since it allows us to control the bias and at the same time enjoy the decrease in the MSD at high eigenvalues due to the regularization term. Also here, as you can see, from the right plot, from the closed form expressions of the performance, I can get curves for the bias variance trade-off for a general R of lambda. Now we can move to multitask learning under subspace constraints. As you will see, this framework can be applied in multiple scenarios. I will highlight here the important concepts, but for the technicalities, you can check the works listed here. In multitask learning under subspace constraints, the calligraphic W is required to lie in the range space of a matrix U. This matrix U has a full column rank. Its number of columns is much smaller than its number of rows. So if we consider here the projected gradient descent solution, we obtain the centralized solution written here. Inside the parentheses, we have the gradient descent step, which can be implemented in a decentralized manner since the costs are separable. And then we project the results onto the range space of the full column rank matrix U. The projection step here, as you can see, is highly centralized since it requires projecting onto the range space of U. And this projection operator is in general dense. To get a decentralized algorithm, we will replace the orthogonal projector here by a matrix A, such that the k-th block of this matrix is 0 if node K and L are not neighbors or are not connected. The second condition is that a to the power of I when I goes to infinity should be equal to the projector of the range space of the matrix U. So the idea here is to minimize the costs in an iterative manner and to project in an iterative manner. By doing this, we will end up with two steps: the self-learning, which consists of the stochastic gradient descent, and the social learning. In the social learning step, node K collects the intermediate estimates size from its neighbors and then combines them through the blocks KL of the matrix A. Once we design the combination matrix A, these coefficients can be used to run the decentralized algorithms that you are seeing here. Now, how to design this matrix? In general, feasibility and optimization problems can be formulated to find a local A such that if we apply this A an infinite amount of time, we will converge to a projection matrix. It can be shown that in the limit when I goes to infinity, A to the power of I converges to a matrix PU if and only if the matrix PU is idempotent, which is the case of the orthogonal projector, and if the matrix A is such that A times PU is equal to PU, PU times A equal to PU, and the spectral radius of A minus PU is strictly less than 1. So if we further assume here that the matrix U is semi-orthogonal, which means that their columns are orthonormal, we can write this feasibility problem that you are seeing here. So this feasibility problem tells us that our A must be local, so we have the sparsity constraints on the non-neighborhood nodes. It tells us that A must have at the eigenvalues 1 the right eigenvectors given by the columns of U, so that AU times AU equal to U, and the left eigenvectors at the eigenvalues 1 are given by the matrix U transpose. The third constraint tells us that the A must have P eigenvalues at 1, where P is a number of columns in U. All other eigenvalues of A should be less than 1 in magnitude, so that the spectral radius of A minus PU is strictly less than 1. Now, the feasibility of this problem will, of course, depend on the graph structure or network topology and on the dimension of the range space of the matrix U. In general, we have this problem to solve, but in some situation, it might be possible to simplify this step by choosing an A that satisfies some simple conditions, as you will see in the following. So, as I explained previously, if we take the smoothness case, we know that the solution is almost sparse in the spectral domain, as you can see from the figure here. So the idea here is to formulate multitask problems where the solution must lie in the range space of a matrix U, which consists now of the first eigenvectors of the graph Laplacian. In the single task estimation, on the other hand, we would like to project onto the range space of the matrix U that enforces consensus on the parameter vectors. So we choose the U proportional to the vector of all ones, as you can see from this figure. The Kronecker identity is here to handle the vector valued W's at the agent. It's common in the literature to choose an A that is doubly stochastic in order to handle the single task or consensus requirement. Since for a doubly stochastic matrix, we know that it has the columns and rows adding up to 1, and an eigenvalue of 1 with multiplicity m, if we have this Kronecker I here, and all other eigenvalues strictly less than 1 in magnitude. We have many rules in general for choosing a double stochastic matrices, so fixing the combination coefficients in the case of single task estimation is a simple task. This is also the case in multitask learning with overlapping parameter vectors. This situation arises in power system state monitoring application. So in the example here, we have an IEEE 14-bus power monitoring system, which is partitioned into 4 areas. Each area has its own control center. So in this application, the bus voltages to be estimated at neighboring areas are partially overlapping due to the fact that the areas are overlapping. Consensus needs here to be enforced on the overlapping parameters, as you can see from this application. This consensus can be enforced by requiring the polygraphic W also to lie in a low-dimensional subspace that has a particular form, as you can see in the figure to the right. Here, also to reach a consensus on a given parameter, we combine in a convex manner using non-negative coefficients A, superscript n now, the intermediate estimates of this particular parameter at neighboring agents. So now per parameter, we can choose a doubly stochastic matrix. Therefore, it is enough here to choose a doubly stochastic matrix A per parameter to be estimated. We might apply the framework in other applications, such as in beamforming applications, where the objective is to estimate a signal coming from a source located at a given angle, and to remove the interference part coming from sources located at other angles. So we tackled this problem from the linear constraint minimum variance concept, where we need to project onto a linear equality constraints, and we observed a good performance results when the beamforming problem is formulated and solved in a decentralized way, as you can see from the figure. which represents here the signal to interference and noise ratio. Performance-wise, when you analyze this algorithm with respect to the solution W star of this problem, we found that the decentralized solution attains the same MSD performance as the centralized one under some assumption on the costs, gradient noise, and so on. So I will not go into the technicalities, just I would like to emphasize that the performance is on the order of mu, as you can see. So the smaller mu is, the smaller the MSD will be. Also, the performance depends on the data characteristics given by the Hessians at the solution and the gradient noise covariances also at the solution. Now, as you can see also from the steady state, mean square deviation, we have the trace of the inverse of the Hessian in the range space of the matrix U multiplied by the covariance of the noise in the range space of the matrix U. So the performance will depend on our data characteristics in the range space of our matrix U or in the useful range space. This result is expected since we are removing the content that is outside the range space of our matrix U. Now, I will end the webinar by quickly describing an interesting situation where we need to both project onto a range space of a matrix and at the same time enforce smoothness assumption by regularizing. So here in a clustered multitask formulation, the nodes are decomposed into several clusters, and within each cluster, as you can see here, nodes are interested in estimating the same parameter vector. The tasks are at different clusters here are different, of course. In the current setting, for example, we assume that at two different clusters, the parameter vectors to be estimated share a large number of identical components, and they have a very small number of different components, as we illustrate to the right here. In such applications, what we really need is to reach a consensus within a cluster. So this consensus requirement can be written in terms of some subspace constraints. Now, for the regularization term R, the focus here is on the case where we want to promote piecewise constant transitions between the parameter vectors at neighboring clusters. So here what you can do is to use the L1 norm of the difference between WK, for example, and WL, where the rho KL here in the equation is a local regularization parameter. It is over an intercluster link connecting two neighboring nodes K and L belonging to two different clusters C1 and C2. Therefore, over intercluster links, we enforce here piecewise constant transitions, and over intracluster links, what we enforce here is a consensus constraint. Deriving an algorithm to solve the multitask formulation in this case is challenging due to the non-differentiability of the regularizer, of course. But interestingly, one can show that a closed form expression exists for the evaluation of the proximal operator of a weighted sum of L1 norms. So here, by minimizing the global cost using the proximal gradient approach, we obtain an approach consisting of two major steps. The first step, which is the self-learning step, it's as usual. And then we have the social learning step, which is now decomposed into two sub-steps, the intra-cluster social learning step and the intercluster social learning step. In the first step, we have a combination step where node K receives the psi's from its neighbors that are inside the cluster and combines them in a convex manner in order to reach a consensus within a cluster. The result is called phi K. And then in the second step, which is the proximal step, node K receives from its neighbors that are outside its cluster the phi's and computes the proximal operator of the function G, where here it has this form. It is a weighted combination of L1 norms, and we know its proximal operator. Now, this algorithm that you are seeing here was applied in a compressed sensing application, But due to time limitation, I will not go into the details of this application, but this is one application for the algorithm. Now, that brings us to the end. So today we saw decentralized learning over multitask graphs. We saw that whenever we have a multitask network with some prior information on the relationship between the tasks, we need first to study how these relationships can be promoted. Then we need to solve the problem in a distributed and adaptive manner. We also need usually to analyze and conclude about the benefit of multitask learning, of course, compared to non-cooperative learning. Usually the multitask learning is promoted through the cooperation, which can lead to different social learning rules depending on the prior information, as we saw today. In the smoothness case, for example, the cooperation will steer the network toward output smoothing. Generalization are possible in the smoothness case, as we saw, through the graph spectral regularization. And then in the subspace projection case, the cooperation steers the network toward the projection onto the range space of the matrix U. Here I'm listing the different references mentioned throughout this webinar. And finally, please, if you have any question, feel free to ask. Thank you for attending.